We'll head over to our next presenter for the evening, André. Welcome, André.
Hello, can you hear me?
Yeah.
All right.
We hear you. Yay, welcome, André. And I'm really
Thanks.
happy
Thanks,
to
Magnus.
say that, yeah, you're welcome. You're actually a colleague of mine, so I'm super thrilled that we colleague. And also, I'm going to go ahead there ahead of your presentation and say that you're actually presenting part of what's been your master thesis. So that's really cool. Yes.
Yeah.
Yeah.
It's a small part, but hopefully it'll connect nicely
Yes.
to the meetup.
Thank you. Yeah, the stage is yours. Hit it away.
All right. Um, uh, I think I'm getting some audio there. So can I start? All right. Um, all right. Thanks, Magnus and Beat and Func Prog Sweden for the introduction. So I'm going to talk about this little concept here of polynomial functors and why it's a jackpot. And I'm here representing Alabit. I work there as a functional programming consultant, and I'm also showing off some of the work I did as part of my master's thesis at Chalmers University. Uh, all right, so okay. So a little bit of background on me. I'm a programmer. That's what I do by trade. Uh, uh, and I've loved Haskell, the programming language, ever since I first came across it. I think it's quite a beautiful language. It's uh, uh, just include a little snippet of code here. A lot of people are going to be familiar with that. And I've also had a sort of a parallel or dual love or interest. Sorry, I'm getting some audio. I'm getting some. Uh, uh, sorry, I'm hearing some audio back, so it's a little distracting. But all right. So anyway, some background on me. I'm a programmer. I've always loved the Haskell programming language ever since I first came across it in university. And but I've also had this sort of parallel uh, interest, you could say, in complex systems, which are systems that basically have simple parts, but when they combine and are allowed to interact, the simple parts are allowed to interact with one another. They give rise to some complex behavior, like this little diagram shows of emergent global structure. And I've always had this sort of nagging feeling that, well, Haskell is a language that is kind of known for abstracting a lot of stuff away and finding and distilling different patterns of abstraction in different, programming contexts. And complex systems is also kind of about these abstract structures or some structural similarities that just show up in physical systems in the real world. It's a very physics-oriented discipline, but they've always had this kind of thing in common of similar abstract structures appearing in different places, and this kind of led me to find a very nice synthesis of these two fields, these two interests, which is in the topic of applied category theory. Um, uh, a lot of people might have heard that Haskell is very influenced by ideas in category theory. And I'll get into what applied category theory is, but the way it connects directly is that it's basically the topic of the master's thesis. And I'm going to show a technique or this particular category and how it can be used to give you a better sense of this connection. So what you need to get the most out of this talk, some background for the reader, for the people watching, is I hope you have heard of category theory before. It's I'm not going to go into any heavy categorical stuff, or I'm not going to go into any more detail than necessary for the point I'm trying to make. But it's good if you know that it's about objects and morphisms between the objects, and crucially, it's about what happens when you compose morphisms from one object to another. So in this little diagram here, you have a morphism or an arrow or a map, it's also called, from A to B, one from B to C, and that forces the existence of G after it, the composition of these two arrows. Another thing that will help you get the most out of this is to know that there's an algebra of types or sets. Really, you can think of types as a collection of values. So they map pretty nicely to sets in mathematical set theory. And the previous speaker, Adrian, actually did me a big favor in explaining and going into quite a bit of detail for what it means in programming for the fact that this algebra of types exists. This is a very deep fact, one of my favorite facts about the universe. And also, I hope you are familiar with Haskell's basic syntax, and this declaring some data types here and defining a function. And I also hope that you can look at some Agda code and not be, sort of freaked out by it. It has a pretty similar syntax to Haskell, but it has dependent types, which is basically, you can kind of think of it as a super Haskell. That's how I market Agda to my programming friends. It basically means that a type of value can depend on on some other type's value. And this is some Agda code declaring a record here. So a product type. So starting with some motivation for why apply category theory is relevant at all. So category theory, pure, is about patterns in different areas of math. The field was invented because people would find, there's this theorem here in group theory, and there's this other theorem here in topology, and there's this other structure over there in abstract algebra, and they kind of remind, there's a sense in which they remind one another of they look similar. And is there a way to make this connection precise so it doesn't just live in this sort of fuzzy intuition space? And it was very successful, and this was invented, I think, in the 50s. And now it's a field of math on its own right. And what I would say is that there is a categorical mindset. It's a way of seeing things. You focus on compositionality, what it means for two relationships, or two, technically speaking, they're morphisms or maps, but these arrows that go in between objects. What happens when you compose them? What happens? What does it mean for these arrows to compose and have some meaning in a field over here, to them having this, to them preserving composition, or keeping their structure as you translate between fields. And applied category theory is a pretty young field, I would say. It's about employing this way of seeing patterns into other fields. So not just pure math, not just algebraic geometry or topology, but things like game theory, chemical engineering, economics, statistical physics. The list just goes on and on. If you look for applications of category theory on Google, you'll likely be overwhelmed. This way of seeing, I like to think of it as conceptual plumbing. It's like you're sticking concepts together, and you're focusing on how they fit together and not on what things are. There's a great tweet here about what it does to your thinking for the categorical outlook on the world, on science, and knowledge. And there's these great talks here for very concrete examples. They go on to a lot of detail of what this means. One is just how it helps you think about a problem domain, and one is just in software engineering examples, really. And oops, I have to zoom out, I guess. And by representing things in these categorical terms, they can be seen as a part of a larger context or a universal language that is very formal and very precise. But this can be really hard. There's a quote here. This is on the category theory Zulip, which is like a Discord or a public chat room. And a lot of working category theorists are there. And this guy here, John Baez, is a legendary figure in this field. And it sort of speaks for the statement lands, because sometimes the connection between how you can formalize something in categorical terms is just really far away from the reality of the model. It's like the particular abstraction that the thing tends to map to, or sometimes it's just not clear and you can't really use it. Except that sometimes a really, really good and powerful abstraction or way of seeing, to keep with this theme, comes along. And this is polynomial functors. And I'm giving you a list here of different things that it either models directly, or it applies to, or is related in more or less straightforward ways. These here are some visualizations of them. I'll explain what this means in a second, but this is this list here is non-exhaustive. I mean, people are finding new applications of this concept all the time. And what I hope to give you from this talk is just an inkling or some instinct that we're onto something. The first time I came across this concept, I didn't understand what was going on. It was hazy and confusing. I'm like, how does it work? So I don't expect you to come out of this like, yes, I know I can use polynomial functors anywhere now. I'm trying to give you a sense of their power. But before I introduce polynomial functors, I just want to give a little more perspective on regular functors. So functors are this concept from category theory, which is for our purposes, we'll just talk about the category of sets or types. So they act on types, right? Like a function sends a value to another type, right? Like this function here sends every integer to its successor. So 1 gets sent to 2, etc. A functor sends a type to another type. In the case of the list functor, which is the one most functional programmers are going to be, it's a pretty straightforward example, I think, or I hope. The type int gets sent to the type list of int, so list of integers. String gets sent to list of strings, etc. And functors also have the property that they act on functions on the original type to functions on the target type of functor. So if you have a function that is a type int to string, then fmap of that function, which is applying the action of a functor on the function, is going to have type f of int to f of string. In this case, f would be list. And there's some drawings here to help you visualize this. So what are polynomial functors? They are a specific type of functor. They're a specific subset of them, you could say, that send the source type to a target type that combines the source in a limited way. These are basically the only operations that we can use. It's summing, multiplying, and raising to the power, exponentiating. This is in the sense of the Curry-Howard isomorphism, which is that what gives us that algebra of sets or of types that algebraic data types are based on, and that Adrian actually explained in his talk. And a convenient way of representing representing polynomial functors is as dependent pairs. So it's one set, and then for every element of that set, it's another set. So there's a visualization here. These are called corolla forests. Corollas are trees of depth 1, so these little forests of little trees here. And this one has a set of so-called positions, and each position has a set associated with it. So this one position has a set with 5 elements. This other one has a set of 2 elements. This other one also has a set of 2 elements. This one has 1 element. And there's 2 ways to, here's 2 examples of ways to write these. One is in Haskell. This is a regular data type. You could derive the functor instance for this automatically. So this one is one type. The first type valid constructor has 1, 2, 3, 4, 5 copies of y, the thing that the type that the functor acts on. Second one has 2, etc. And you can also write these algebraically. And then importantly, the numbers here mean sets with that many elements. So this is y to the power of the set of that many elements. This is we're only using the stuff that we're allowed to in this setup here. The set of positions is a set of sum ends in an expression like this. So this one has 4 sum ends. This one has 5. That's the set of positions. And the direction at a given position is the exponent of that sum end. So this is a polynomial functor. And we can map between polynomial functors. If you know a little bit of category theory, or perhaps you've done some more advanced Haskell, these mappings between functors, you might expect that they're natural transformations. But they're actually called, for our purposes, we'll call them dependent lenses. And yes, there is a connection with Haskell lenses, but don't worry about it. That's I can answer questions about it later if anyone cares, but we're not concerned about fetching data inside of deeply nested data structures here whatsoever. It's just to think about them as natural transformations. And the dependent lens has this map forward on position. So this is represented by these 4 arrows here with our previous example. And then for every one of these mappings, you need a map back on the directions at wherever you landed. And if we look at this map in Haskell, this is what we see. These are from our Haskell definitions before. This is exactly the map here, actually. So the first thing is the pattern match on the constructor of the first functor, the first constructor, and this you have to choose one of the constructors in the target functor, which is Q here, and that's the first step in your pattern match. And then you need to fill the slots of that value constructor. If you remember, QA has 3 directions, and that's what is represented here. So QA 1, 2, 3. So for each one of these, you have to choose one of your Y values to fill it up with. And this is how the map back is working. For every one of these slots, you have to pick one of 5 different choices. And the same for all the other constructors. So functors, polynomial functors as objects, lenses as morphisms. This gives us a category, the category poly. But the Haskell way of working with these polynomials is pretty limited, because polynomials can have any type as a position or sum end. And in the case before we were just showing, they were finite types that we know every element of the type, so we can just work with them directly. But this is a coherent expression. This is a polynomial functor, but it's not really clear how you do this in Haskell, at least not to me. People are trying to do it. Iceland Jack is a more or less well-known figure in the Haskell ecosystem, and every once in a while he posts stuff on Twitter on trying to follow the source that I follow for my master's thesis, but it's not clear how to do this. I guess this is a valid representation, but for me at least, it's not clear how to. I don't even really know what I'm looking at. And lenses or mappings between these functors are going to be even harder. So enter the Agda programming language, which is dependently typed. this is really a much more natural way of expressing the category poly, that's a sort of polynomial ecosystem. And Agda looks pretty similar to Haskell, I would say. This record is basically except you can give names to the field, so it looks a little nicer. I think it's more usable. And this is a polynomial, so you have a set of positions, and for every position in this set, so this is how dependent types come into the picture here, you have another set. So if you give me one of these positions as an argument to the field direction, I'll give you back a set. And a lens is also a dependently typed construct. And you have, again, you have two polynomials from and to. There's a map on positions, position from to position to. So this is the map on the going, this is the map going forwards. And then there's the map on directions going back. So given that you start at one position, and given that you have a position at which you start, and you have a direction at the target polynomial at a mapped position from where you started, I'll give you back a direction in the one you originally started. So this is the map backwards. This might be a little tricky to wrap your head around, but again, it's about the inkling. And after working with this for a while, you start to wish every programming language had dependent types, because you often forget how much power you have actually. It's so much power that Agda can actually be used for proving theorems, just stating mathematical theorems and constructing proofs. And this is also part of my master's thesis, to prove a bunch of categorical properties of the category poly. But now I want to show enough math, or that was enough math. I want to show how this is actually useful and apply to something. And the application that I know the most about, that I've written the most examples for, are dynamical systems. So a dynamical system is a very general, sort of loose thing. It's defined as basically a process that evolves in some state space. And the state space is going to be a set also. In this case here, this is just a little picture showing the dynamics of a particular system. And this system, if you start with some initial condition or some initial state, it's going to traverse the state space in a certain direction. In this case, it's like a two-dimensional. I think this is R squared, so it's like the state space is pairs of real numbers. But there's also such a thing as an open dynamical system. So what if we don't want to just let the dynamics run in time? We also want a notion of providing an input to the system at every time step. This is showcased here. So when you're on state 0, if you give the output, if you give the input 1, then you're going to traverse to state S1. But if you give the input 0, you're going to stay at S0. And this is a little automaton that is sort of gives the idea of what an open dynamical system is. And this, one way of formulating this is as a Moore machine, which is a very general kind of thing. Many things can be modeled in terms of Moore machines. If I understand correctly, there's still study to this day in automata theory. And Pauli's dependent lenses, the thing that we showed, we gave the data for a dependent lens, actually models Moore machines very well. You don't even need all the power of Pauli. You can get away with a non-dependent version of it. But just to stay in the Pauli land here, lenses of this form. So if you have some state type y, some state type multiplying your variable y, and then raised to the power of that same type, you have a lens from this thing to some other expression here, so an output type times y raised to an input type, that can be interpreted as a Moore machine or an open dynamical system. And so here's a little box showing this. It's like it's a this is something like this would be, so this is the output type. So this would be IO int multiply y raised to the power of top, and this is the unit type that has only one inhabitant. And one thing we can do is put systems in parallel with this operator here of O times. This is called the parallel product. And this is a categorical construct, but this is the only, I'm pretty sure this is the only categorical construct that I'm gonna, we're gonna need for the rest of the application. So then if you have a polynomial B or P and Q, and P is, has AB in its raised power. So that's its input type, it's pairs of A and B. And its output type is D, and you have Q like this. If you put them in parallel, then you get something that takes an A, a B, and a C as inputs, and it produces D, E, and F as outputs. And then, so that's polynomials, and then lenses can be used to wire systems together. So, and this gives rise to a new system. So the idea here is that you have this inner box, which is the dashed line here, and a lens from this inner box to this outer box. This outer box is the expression for it is given here. Takes A, B, C as inputs, produces A's. This wiring pattern itself is a lens in a very precise and specific way. I'm not going to show the code for this. I can if someone is really curious and wants to see what this looks like in code. But this does reduce to just those two functions that compose a lens, a map on positions and a map on directions. Here's another example of a different wiring pattern between the same two polynomials. So it's just an example of a different lens. And some concrete examples of this, of these, the lenses that actually correspond to dynamical systems, are these two here. So this is a little, what we call them wiring diagrams for a Fibonacci sequence generator. This is one of the first examples in the book that I followed for this work. So you have one system that just its only responsibility is to sum its two inputs and then spit that result out as its output. And you have another one that just takes its input, takes an input and produces that input as an output always. This is the identity function modeled as a dynamical system. And if you wire these two systems in this particular way, then what you get as an output of the outer box here is the Fibonacci sequence. So you're summing. It might not be obvious how that is the case now, but again, it's about the input. It's about the idea of the expressive power of this sort of setting. There's another example which is very fun, which is a Turing machine. If you remember your probably some introductory class on the history of computer science. So a Turing machine is made up of an infinitely long tape that can have a bunch of symbols on it. It's called the alphabet set. And it has a processor that interprets these symbols in some way and runs some internal logic. This actually works. You can model a Turing machine in this way with such a wiring diagram. And here's a reason why I didn't actually want to show any Agda code, is because it perhaps would need too much context to explain and to go into and try to give a high-level idea. But if this means something to you, you can copy this code and run this fiblist variable here. Is actually contains the Fibonacci sequence. But here's a bigger example that, again, I'm not going to go into the details, but something that actually uses even more of Poly's power. It's that of a kind of neural network called reservoir computers. And the thing about a reservoir computer is there's a little schematic here showing what it is. And the main thing about it is that it has three basic stages. So when you want to run a program, when you run a reservoir computer to predict some input, as you might know, neural networks learn to reproduce or learn to recognize inputs and produce consistent outputs based on some input. There's a training stage, and then there's something called a touching stage, which is specific to the training algorithm of a reservoir computer. And then there's a going stage where it's actually predicting. So our box is actually changing its wiring pattern. And this is where the category poly as modeling dynamical systems really shines. And there's also code written for this. And this power of expressing dynamical systems that can connect to different things as time goes on I think is just extremely cool. And there's just an endless array of things that can be modeled in such a way that they just change the wiring pattern in time. And just to show that this actually did work is on the left here we have a dynamical. We have a system called the Lorentz system. It has a property. It's called a chaotic dynamical system, and that basically means that it's really hard to predict how it's gonna traverse its state space. In this case, it's R cubed. It's a 3D system, so it's 3 tuples of real numbers. And reservoir computers are used to train. They're trained on values of the Lorentz system in order to be able to predict them. And this is the implementation that I did for my master's thesis, and it just shows the prediction as time goes on. After you train the reservoir, it can actually predict the dynamics of the Lorentz system, so the outputs that it gives in time. And there are more intricate ways of representing the changing wiring patterns in neural networks. As I know, coalgebras in Poly are very relevant to that, but I don't really understand them well enough to explain them to you, unfortunately. But this is just this picture here was actually generated by some Agda code, and it's real. It's a real program that was just uses the category directly in a very ergonomic way. And so what else could we model this way? I mean, I gave a very exhaustive, very potentially overwhelming list of examples in the beginning, but here's some more ideas. I've been thinking a lot about modeling microservices in terms of polynomial functors. Microservices are they are little boxes that speak to one another. They provide input to another one's output, or output to another one's input. They can change their wiring patterns. Microservices talking to this system at this particular state, and then it's not, and then it's changing throughout time. Front-end components are also a good example of this, I think. I haven't explored this line of thinking totally yet, but I've been doing a lot of Halogen, which is a framework in PureScript, where components are modeled it's very composition. So components own their own little state inside them that can be, and they have an input type and an output type. It's shown here, and they have a monad in which they run, and this is not showing the state type. This is part of a different part of the application, but in principle, they are this sort of object where they have a state, they have a notion of what it means to be a state for them, a notion of an input, a notion of an output, and they connect in this way. And hardware circuits just lend themselves very naturally to this sort of exploration, also to this sort of modeling. And there is some categorical work on formalizing circuit diagrams, but I also still don't know that much about them. But yeah, this is a very, very small list of examples. Um, Again, going back to the theme of the talk, it's about giving imagination, as David Spivak, one of the authors of the book, says, um, to, oh, wow, yeah, I wonder what things I'm working with that also sort of fit this general pattern of communicating parts that can change their connections and go in different, have different wiring patterns to them. And that is actually all I have for the talk. And to sort of justify, to give finally explain why I called it a jackpot, is because this is actually a quote in the book. The category poly is a jackpot. Its beauty flows without bounds. And again, didn't understand it the first time I read it. Then I started actually using it in my work, and I couldn't agree more. This is from the authors of the book. This is the main source I would like to point you to. There's also an entire free course, just a playlist on the book. They go through the entire thing. It's pretty heavy on the category theory. It might take several watches, but they do, I think, a good job of consistently keeping it with the connecting it to the intuition behind these concepts. And more generally, the Topos Institute YouTube channel is just fantastic. I can hardly recommend it enough. If this stuff sounds interesting at all to you, I suggest going down that rabbit hole a little bit. And yeah, you can find all the code for my master thesis. You can find in the GitHub, and in the link here. But yeah, that's all I have for tonight.
Thank you very much, Andrea. Thank you. Very interesting. I actually started to read your master thesis in the beginning, and as I said, I think I need some kind of framework before I just go into it.
Yeah.
Gave it. Very good. Thank you very much. We have two questions in the chat, or one thing. Like, now we got to clarify object in category theory, and that it's not object in object-oriented programming.
Yeah. No, it's not. So I'll go back to the little diagram. I thanks for pointing that out. I didn't even connect those dots there. So an object in category, in this case, the objects are A, B, and C, and the arrows are F, G, and F after G. And there's also some identity arrows that are important for, well, they're important. But the object has nothing to do with objects in object-oriented programming. The idea in category theory is like I was, like I was trying to stress, it's about the compositionality. So the objects are supposed to be totally abstract or meaningless in some sense. What matters is the relationship between the objects and the patterns of relationships that form, how we can study those mathematically. The A, B, and C here are kept as abstract as possible. I mean, the arrows are also kept as abstract as possible, but in this particular diagram. But the thinking in category theory is focus on the morphisms. The objects are just there to basically give endpoints to the morphisms. Yeah. So thanks for thanks for catching that.
Yes. Thank you again. How come you come into Haskell programming?
So I got into Haskell. I took a course in university. I went to University for Computer Science back in Brazil, and I took a course called Paradigms of Programming, or Programming Paradigms. And they started just straight away with Haskell. And at that point, we had like, I think 1 semester of some basic C, maybe 2. And I was basically drawn to it because it really destroyed me. I didn't understand the concepts, and I remember the TA even couldn't explain what a monad was, and I was, but people still use this and they swear by it, and and how come the code looks so elegant and beautiful? Well, there must be something to this. And I just kept digging, and yeah, I was hooked.
It's like this mystery you have to unravel.
Yeah, exactly. An adventure.
Yeah. And then you kind of get, I mean, you continued from Haskell into this, like, starting talking about category theory. Is it also like the more you learned, the more you have to, you know, you have to drag this rope, like, where does it go? Where does it go? where's the end? Where's the end door?
Yeah, and the amount of directions you can go just grows as you pull the rope. It just grows more and more. It's an incredibly deep set of subjects. Yeah.
How do you, if you would give an advice to someone that want to learn Haskell, looked at Haskell and felt, shit, I don't understand jack shit of this. Where would you start? Like, to, you know, progress into learning Haskell?
You know, so I think there's two different ways of answering this question. So the people, I'll choose one of them, which is people tend to associate functional programming with Haskell because it's purely functional. It's in computer science curriculums, and it showcases the aspects of functional programming the most. It sort of forces you to do it that way. But what I tend to recommend to people is actually, if you want to learn functional programming, don't start with Haskell. Start with Clojure. Clojure is it's also a functional programming language, but it is dynamically typed. People get stuck on Haskell trying to print something to the screen, or how does the IO monad work? How do I get something out of a monad? And it's just not the right way to think about it. If your program is running on a processor, it is in a monad. Don't worry, like, you just have to inject the behavior in there. But this is too much to throw at beginners, I think. They get sort of lost in the type system. So I think, and Clojure doesn't have any of that. I think it's a much more beginner friendly language that will sort of train you to think in functional terms. And I think the transition to Haskell and the type system and monads and all that there is going to be more natural.
Yeah. Kind of agree. I started myself in other languages and leaned into Erlang. It was quite natural from some languages. Yeah. More, you talked a bit about Agda. How come you was that part of the category theory? So you had Haskell, you had this background, you went into category theory, and now Agda came to you, or you came to Agda?
Yeah. So the Agda thing is interesting. So Agda is actually developed at Chalmers, and I didn't know this. I went for the master's. My master's is in complex adaptive systems. Actually, I didn't connect the dots that the place where I was doing my master's program was actually a big home for functional programming in Agda. And but I still wanted to connect these two things, like the sort of the Haskell / categorical way of seeing stuff with complex systems, and the Agda presence here is just, or at Chalmers, is just so strong that it was kind of a natural fit. And once the authors of the book just said, yeah, don't try to just represent this stuff in Haskell. It's gonna be too hard. Like I showed, it looks weird pretty quickly. Use a dependently typed language like Idris. So Idris was the first thing I played around with dependent types. I knew they were around, but I never tried them. But then Agda was much more natural, and because of the fact that it's developed at Chalmers and so many people who know about it here. So yeah, I think that's how I got into it. There was no other way, really.
Yeah, we had some people here shouting or saying in the chat, not shouting, but saying in the chat, you could also go from Elm into Haskell, and then some other people agreeing with you, like I started out in Clojure and then went into looking and doing the same thing in Haskell.
Yeah.
So thank you very much again, Andrea. Very nice presentation. Thank you very much.
Yeah. Thanks for having me.
Yeah, you're welcome. You're welcome back if you want to present more concepts from your thesis. Yeah. And with,
I'd be delighted to. Thanks.
yeah, great. And with that, we'll end tonight's meetup, and we'll see you again in August. We'll announce like in a week or two when we do the dates in August, September, and then as I said again, if you're in Stockholm in October, come and see us live in Kivra. With that, have a nice summer vacation, everyone, and see you back in August. Bye.